Okay, so in this next video in the playlist on cyclic AMP signaling, what we're going to do is discuss a little bit of pharmacodynamics, and specifically what we're going to discuss is the occupancy equation, so pharmacodynamics. Okay, so what is meant by pharmacodynamics? Well, basically, it's all about how drugs interact with receptors. So pharmacodynamics, the occupancy equation, is what this video is going to be on. Right, and you might be wondering, why are we going to discuss this in a playlist on cyclic AMP signaling? Well, we have just been discussing calcium. And I would like to discuss the difference between two calcium chelators, namely BAPTA and EGTA. I want to be able to explain to you why BAPTA and EGTA can have the same affinity for calcium, and yet BAPTA is much better at blocking calcium signaling than EGTA. And these are both calcium chelators, which means that they just bind calcium, basically. Why is this BAPTA far better than EGTA at blocking calcium signaling than EGTA is? Okay, so to do that, we need to discuss a few pharmacodynamic ideas. So let's begin then. So let's imagine we have a certain concentration of receptors. And remember what concentration means. Concentration means the number you have, usually in moles, per a certain volume. And if I write the concentration of R, that means the concentration of receptors. And what that means is how many receptors do you have, number of receptors, usually given in moles, and it's usually per a litre. So basically, if you have some fluid, then the concentration of receptors is, if you continued that fluid to a litre, let's say, and you kept the same density of receptors basically in the fluid, then how many receptors will there be in that container? So let's say this is a litre here. This is a litre box. Then the concentration of receptors in here is basically just going to be the number of receptors in a mole. Number of receptors where we give that number in moles. Okay, so let me draw some receptors in here. Let's have the receptors in pink. So these little dots represent the receptors in pink. Okay, right. Now, there we go. So these are the pink things. Now, if we add in a drug molecule, and we add in a certain concentration of the drug molecule, and this is the initial concentration of the drug that we put in, then what's going to happen is, again, what that means is, since we're working with a hypothesized litre here, then the concentration in molar will just be the number of moles of that receptor per litre, but we've got a litre, so it'll just actually be the number of moles of that receptor in the number of moles of that drug in this litre of fluid. Okay, so we've got our drug now in the box as well. Right, so if the drug can bind to the receptor, then what's going to happen is some of these drug molecules will actually form a complex with the receptor, and they'll form what's known as a drug-receptor complex. Right, so what's going to happen in this box is that drug molecules can bash into receptor molecules, and those can form a drug-receptor complex. So let's draw a drug-receptor complex. So this is the receptor, this is the drug. So they can collide and form a drug-receptor complex. So if the drug can bind to the receptor, then there is this possibility for forming a drug-receptor complex. Right. So then what's going to happen is, once you've formed a drug-receptor complex, which I'll just denote DR, then what's going to happen is that drug-receptor complex is going to, it doesn't just stay bound forever. Well, some drugs do. Some drugs do bind to the receptor irreversibly and then never ever come off. But most drug-receptor complexes fall apart as well. So this is going to go back to being a receptor molecule, basically, with the drug molecule here. Okay. So here's the drug molecule, and here's the receptor molecule. So basically, there is some rate at which drug receptor complexes degrade, basically. They break apart. So, if we want to know how many drug receptor complexes are going to be breaking apart in, let's say, a second. So let's say we want to know the number of drug receptor complexes that are going to break down in a second. Drug receptor complexes that are going to break down in a second. Complexes which will break down in a second. Break down in a second. Then that will be it will basically be proportional to how many drug receptor complexes you have got in this box. And the number you actually have is the concentration of drug receptor complexes, because I have said we are working in a liter box, basically. So we can just think of the number as being the concentration of drug receptor complexes in this box. So basically, if you double the number of drug receptor complexes you've got in here, the number that will break down in a second is going to be twice as much. So that's why it's going to be directly proportional to the drug receptor complex concentration. Okay, oh sorry, not directly proportional, but proportional, at least, to the drug receptor complex. If it was directly proportional, that would mean that it's actually, the ratio between them is 1. Okay, so, now, all we can replace that proportional sign with is equal to some constant times the concentration of drug receptor complexes. So that basically tells us how many drug receptor complexes are going to break down in a second. Okay, so that constant there is called the rate constant. The rate constant of degradation. So we'll call this rate constant at which drug receptor complexes will degrade. At which drug receptor complexes will degrade. Now, we've kind of attacked this from the wrong way, really, at which drug complexes will degrade, because we've talked about drug receptor complexes degrading before we've actually talked about them forming. So let's talk about the other reaction now. Let's say we've got a receptor and a drug molecule, and they're going to collide together, and they're going to form a drug receptor complex. So we'd quite like to know, well, how many of those drug receptor complexes are going to form in a second? So we'd quite like to know how many drug receptor complexes are going to form in a second. Number of drug receptor complexes which will form in a second. Complexes which will form in a second. So how would we work that out? Which will form in a second? Well, basically, this is going to have to be proportional to firstly the concentration of the drug, because if I double the concentration of the drug, I would expect the number of drug receptor complexes that I'm forming every second to double, basically. And we're also assuming that we are working with concentrations that mean that you aren't saturating this, basically. Obviously, everything I'm saying here is going to break down if you put in so much drug that all of the receptors are occupied. If all the receptors are occupied, then things will break down. But we're going to assume that you haven't done that. Okay, so we're going to assume that we're at concentrations where if you double the drug, you're also going to double the number of drug receptor complexes you're forming. Also, if you double the number of receptors, you would expect to double the number of drug receptor complexes which you will form in a second. So, this tells us that this should be equal to some constant times the concentration of drug times the concentration of receptors. What else should it depend on other than those two things? You might say, well, surely it depends on the affinity that this drug has for this receptor. Well, that's taken care of in this constant. That constant will change depending on how much the drug wants to bind to that receptor. Okay, so I'll call this, we've now labelled two different Ks here. So I'm going to call this one K1, I'm going to call this one K2, because K2 is the degradation, and K1 that's why I've called them K1 and K2, because this one comes before K2. Okay, right, so this is going to be the number of drug receptor complexes which will form in a second, and this is going to be the number of drug receptor complexes which will break down in a second. So, once this reaches an equilibrium, basically what's going to initially happen is when you put in your receptor and then you put in your drug on top of that receptor, initially you'll have all of the drug molecules apart from the receptor molecules. However, the drug molecules will start to bind to the drug receptor molecules. and you'll start to get more drug receptor complexes and obviously lower concentrations of free drug and lower concentrations of free receptors. Now, what will also happen is the drug receptor complexes will gradually break apart and return to being free drug molecules and free receptor molecules. What we want to know is at what concentration of free drug and at what concentration of free receptor and at what concentration of drug receptor complexes is it at equilibrium, i.e. when does the number of drug receptor complexes being formed equal the number of drug receptor complexes being broken down, i.e. at equilibrium. If I draw another picture down here, at equilibrium there's going to be certain amounts of drug, which I'm just going to draw them now as DD. So there's going to be a certain amount of free drug. There will also be some drug receptor complexes in there. Here we are. And there will also be some free receptor molecules around. What we want to know is what concentration of drug should there be, what concentration of receptor should there be, and what concentration of drug receptor complexes will there be when it's at equilibrium. And at equilibrium, what's happening is that you're not changing these concentrations. Basically, the number of drug receptor complexes that break down, which is here, should equal the number of drug receptor complexes that are being formed, so the concentrations don't change. So initially, remember, the concentrations were changing. When you just add the drug in and you add onto the free receptor, then what's going to happen is that the concentration of free drug is going to go down, the concentration of free receptors is going to go down, and the concentration of drug receptor complexes are going to go up. Now, that will continue on until you reach an equilibrium point, where the concentration of drug has gone down, the concentration of receptor has gone down, and the concentration of drug receptor complex has reached some level. And that's the point at which the rate at which you're breaking down drug receptor complexes is equal to the rate at which you're forming drug receptor complexes. So this should equal this. So K2 times the drug receptor complex should equal K1 times the concentration of drug times the concentration of receptor. Now, I think it's very, very important to make a big distinction here. These concentrations of drug and receptor are not these concentrations. These are the initial concentrations. So I put in an initial number of receptors into this liter. That's my initial concentration of receptors. This is my initial concentration of drug. That's how many drug molecules I put into this liter, basically. These are not those same values. These are the concentrations at equilibrium. So I might put EQ to stand for equilibrium. And this is the concentration of drug receptor complexes at equilibrium. So these will be smaller than these because some of the drug and some of the receptor is no longer as free drug and free receptor, but is instead at drug receptor complexes. So both of these numbers should have fallen by the same amount, basically, if a single drug molecule binds to a single receptor molecule. Okay, right. So now all we need to do is take all the concentrations to one side and take these two constants to the other side. So we can rearrange this. We can divide through by K2, and on this side what we'll get is K1 divided by K2. Now we can divide through by the drug concentration and the receptor concentration at equilibrium, and on this side we'll get the drug receptor complex concentration at equilibrium, so this bit, divided by the concentration of drug at equilibrium times the concentration of receptor at equilibrium. Okay, right. So now this ratio between the forward rate constant, this K1, and the backwards rate constant, K2, that is called the affinity constant. Usually you call that the equilibrium constant in more general equilibrium reactions like this, but in the case of receptors, that is called the affinity constant. So the affinity constant is the drug receptor complex concentration at equilibrium divided by the drug concentration at equilibrium times the receptor concentration at equilibrium. Right, now what we're going to ask when we try and create the occupancy equation is we want to know the occupancy, which is usually denoted by alpha. Now, what does the occupancy mean? It means how many receptors, what fraction of the receptors are occupied. So it means of all the receptors that we initially put in, at equilibrium, what fraction of them are bound to drug? So basically it means look at all of these receptors that are in here. What fraction of them are bound to drug? I.e., if we look at this population here of the receptors which are in drug receptor complexes, what fraction of the total population of receptors does that population of drug receptor complexes form? So what we want is we want the number of drug receptor complexes at equilibrium divided by the number of drug molecules at equilibrium, which is, remember what that is, that's the number of free drugs. So this is effectively this population here, these receptor molecules that are still free. So that means that, and then what we want to add it to is the concentration of drug receptor complexes at equilibrium, which is that green population. And basically, if we add those two things together, that's going to give us this overall population of entire receptors. So it's important to recognize that this doesn't mean the total, this does not mean the pink, basically, the lighter pink. That means the red. That means the free receptors at equilibrium, not the total number of receptors in our container. The total number of receptors is the total number of free receptors plus the total number of receptors involved in drug receptor complexes. Now, if we want to know the fraction of total receptors that are in drug receptor complexes, all we need to do is take the number in drug receptor complexes and divide it by the number that are in totally in here. Okay, so we somehow need to get this. Now, we can rearrange this equation here. We can say that the drug receptor concentration at equilibrium is equal to the affinity constant times the drug concentration at equilibrium times the receptor concentration at equilibrium. So all I've done is rearrange that equation. So I've just taken these two things to the other side, and now I've isolated what this is. Now if we plug that in to this equation here, then let's see what we get. So plug this in here at the top. We get that it's Ka times the drug concentration at equilibrium times the receptor concentration at equilibrium. And I do apologize, that should have been the receptor concentration at equilibrium, not the drug concentration. So this pink is the number of receptors, free receptors, not the number of free drug molecules. That would have been this, and this. No. Okay, I do apologize for that. So receptor concentration at equilibrium times the concentration of receptors at equilibrium plus, and now we're substituting this in again here, so we get Ka times the concentration of drugs at equilibrium, and again times the concentration of free receptors at equilibrium. And now you will notice that something cancels in that equation. This here cancels, this here cancels, and this here cancels. So the concentration of receptor at equilibrium, basically all we've done is divide the top and the bottom by the concentration of receptor at equilibrium. And what we get is that it should be the Ka, the affinity constant of the drug receptor interaction, times the concentration of drug at equilibrium over 1 plus Ka times the concentration of drug at equilibrium. Now, that is not quite the occupancy equation. That is in the ideal world, how you would calculate occupancy. If you wanted to do this experiment perfectly, what you would do is you would put in a certain concentration of receptors and you'd put in a certain concentration of drug. And you then let it reach an equilibrium and you'd measure the concentration of drug in the concentration of free drug once you've reached equilibrium. And then if you knew the affinity constant for the interaction, you'd then plug this in and you'd work out what the occupancy of your receptors was. That's not how you do it, because measuring the concentration of drug at equilibrium is difficult. However, we know what concentration of drug we put in, so instead what we do is we slightly cheat. We say, okay, in here I'm just going to put the drug concentration that I used initially, so I'm going to turn this into, so I shouldn't put equals, I should put is approximately equal to Ka times the drug concentration that I put in initially, which I knew because I put it in, divided by 1 plus Ka times the drug concentration that I put in initially. And that's what people use when they use the occupancy equation. They use that form. They use the drug concentration that they initially put in. Now, why is that an okay approximation? Well, the reason is that in these sort of experiments, this affinity constant is usually absolutely tiny. It's usually really, really small, usually 10 to the negative 8 or something around there. And what that means basically is that drug-receptor interactions are very, very unlikely. So you have to put in absolutely huge concentrations of drug compared to the concentration of receptors that you put in. So you might have to put 10 receptors in and then 1 million drug molecules in to get them to actually interact with the receptors. Okay? So the scale of the concentration of the drug compared to the scale of this concentration of receptor is immense, basically. So when you actually consider how many of these drug molecules leave the free drug population to become these drug molecules which are bound to the receptor, it's tiny. So the drug receptor concentration compared to the free drug concentration is tiny. So the amount by which you have to decrease the drug concentration from the initial drug concentration to get to the equilibrium drug concentration is tiny, because an equilibrium drug concentration, remember, is the initial drug concentration. Subtract, so this is the initial drug concentration, subtract the concentration of the drug receptor complex, assuming that a single drug receptor, assuming that a single drug molecule binds to each receptor, then basically the number of drug molecules that leave the free population from the number that you put in initially is the number of drug receptor complexes you form, because basically at equilibrium, the total number of drug molecules that you added originally is the number that are free, which is this, plus the number that are in drug receptors, and that's the same mathematical relationship as is there. Okay, so basically this number is tiny usually compared to this number, so it makes no difference to this equation usually if you use the initial drug concentration or the equilibrium if you use the initial drug concentration as opposed to the equilibrium drug concentration. If you have, and these are very rare, occasionally you have drug receptor interactions that are extremely high affinity, then this model breaks down. If you have drug receptor interactions that are extremely high affinity, then this model breaks down for precisely that reason, that you cannot use the initial drug concentration as an approximation for the equilibrium drug concentration. Moreover, there are other reasons why it breaks down. These things start to break down. Specifically, this one starts to break down if you get to too high affinity interactions, because basically if you do occupy all the receptors, then this isn't going to work anymore. I mean, if all your receptors are occupied by drug molecules, then doubling the drug concentration isn't going to double the rate at which you form them. Once you've reached that saturation point, then this equation starts to break down, basically. But usually this is a valid mathematical model. So it would usually be written that the occupancy is the affinity constant times the drug concentration, where you would use the drug concentration that you initially put in, divided by 1 plus Ka times the drug concentration. And you will notice something very odd here, that nowhere in this equation is the concentration of receptor that you put in. So that tells you that the fraction of receptors that will be occupied by drug molecules at equilibrium is not actually affected by the concentration of it's not actually affected by the concentration of receptor. Remember what this tells you. It doesn't tell you how many drug receptor complexes you'll have. It tells you the fraction of receptors that will be occupied, basically. So the fraction that you have doesn't actually depend on what concentration you have. So whatever concentration you have, let's say the receptor concentration our initial receptor concentration is this, then the number of receptors that will actually be occupied at equilibrium is just this fraction times that concentration, and the fraction doesn't depend on that concentration, basically. Okay, so that's that's pretty much the occupancy equation covered. In the next video, what we'll do is we'll actually talk about we'll actually talk about BAFTA and EGTA.